Yes, we can start now. The time is 3 p.m. and I welcome you all to the TA live session on the week 2 content. Okay. So right now we are in the course Technique of Material Characterizations, and currently we are in the week 2 of it. So let's see what are the things that has been covered in the week 2. In week 2 we have talked about the bright field and dark field microscopy, the way we generate the contrast. Is what defined as the bright field and the dark field microscope. Then we talk about the phase contrast microscopy. Like different phase will have different refractive index, and depending upon their different refractive index, different thickness, they will give some phase contrast. Next we talk about the polarized light microscopy, then differential interference of contrast microscopy and fluorescent microscopy. Okay, so these are the list of the 5 microscopy technique that we have learned in this particular week too, and in depth we have understand the concept, and now we are going to solve a few questions based on this. So our entire discussion today, maybe 1.5 or 2 hour, it will based on this particular 5 concept that is right in front of us. So before I start with the lecture, before I start with the doubt solving, before I start with the questions, let me ask you that, do you have any questions in this particular week or in the week 1 that has been covered in the last week? If there is any question, feel free to unmute yourself and ask me. Second, you can also put it onto the text and I will definitely respond to that. Okay, so is there any question? Okay, since there is no question, let's start with the dot solving session. We'll start with a few questions. We'll start with the first concept, let's say bright field and the dark field microscopy. So what's my plan is that one by one we'll quickly have a look onto the concept that has been covered, and then we'll solve the question based on these particular concepts. After that, we'll have a quick revision of this particular concept, and then we'll solve again the question of this. So on and so forth, we'll do this for all these 5 different microscopy. Okay, so let's start with the bright field and the dark field microscope. See, in any optical microscope, whenever we are placing the specimen, let's say we are using in the bright field. So in more or less, like all of us has used the optical microscope at some point of the research or even in the 10+2 class. So there, what we are using is the direct beam, the bright field we are using. We are placing the specimen under the optical microscope and under the objective lens, and then we are analyzing it how it is looking. So more or less our specimen will look something like this. So there is what is happening that the light, which is the direct light, which is coming from the light source, after it go to the condenser lens focus it to the specimen. From the specimen, whatever the direct light is there, we are capturing it to the objective lens. So this is the one objective lens. So this objective lens is the one who will collect the data, who will collect the signal, and it will give us the image, which we can see through the eyepiece. So in the bright field, what is happening that the direct light, this entire thing, the direct light which is reflected, we are using it. Now, this is what normally we do. Now let's go to the dark field. Let's go to the dark field. We know in the specimen we have the grain boundaries. So the grain and the grain boundaries, they will interact with the specimen in the different way depending upon their height. Okay, let's say the grain is at the more height and grain boundary is at the lower height, because we have eased it. Grain boundary is what? It's the east section. We have removed it. So it's comparatively at the lower. So it will scatter the light in the different direction. Right. So the scattered light or the diffracted light, we can say, that light we are passing through the optical. Now we are allowing only the we are allowing the scattered, or one can say diffracted, to pass through the optical. So now what we are seeing is that, see, this is your direct light. This is what you see in the optical microscope. Let's say I keep my objective lens over here. So what I will see the direct beam. Now I tilted my objective lens, I kept it over here. Now what I am seeing is the ray which is diffracted in the different direction. And what is the one? Who are the one who are diffracting it? It's mostly the grain boundary, the surface which are uneven. Okay, those are the things. So this thing is carrying the information. The intensity of this is far lower than this. Okay, so now we can see that, so whatever the thing, the boundaries which were there, which are not as prominent over here, it is more prominent and it's more easy to see in this dark field microscopy. So this one is a bright field microscope image, this is a dark field microscope image of the same specimen, of the same feature, just taken in the different mode. Oblique mode is somewhat, we can say that, okay, somewhere in between the bright field and the dark field. Am I clear? Any doubt in this? Whatever we have discussed till now? Okay, since there is no doubt, let's move ahead. Let's try to solve few questions based on the concept which we have learned. Okay, here. What is the primary difference between the reflected and the transmitted light microscope? The reflected microscope and the transmitted microscope. So we know that we have the specimen, and then what we can do, we can shine the light from the top. It can go to the condenser lens. What condenser lens will do? Condenser lens will condense the entire beam over the specimen. Let's say right now we are talking about the transmission mode. So in transmission mode, now the light will be scattered, or we can say the diffracted, the direct beam we are going to see. Now here is the objective lens. Now this objective lens, yeah. So now this objective lens is going to focus it onto the plane where we are going to see this. Okay. So now in the transmission mode, what we have saw that, let's see the first question. Reflected use electron beam, while transmitted use the light. What our question is that, what is the primary difference between the reflected and the transmitted light microscope? The reflected and the transmitted. The first one is saying that reflected use the electron beam while the transmitted use the light. What do you think? Is it correct? The first option. Obviously it's incorrect, right? We are talking about the light. So the optical microscope can operate in both the cases. It can operate in the reflected as well as it can operate in the transmitted. So what will be the right answer? So the first one is incorrect, right? So in the both cases, we can say that it will be light only we are going to use. We are not going to use the electron. Second, a reflected microscope. In reflected microscope, light source and the objective lens are on the same side of the specimen. Reflected, the light source. Light source and the objective lens are on the same side of the specimen. Is it true? So what we are doing that, in the reflected mode, the condenser condense the light over the specimen. Now the light is again going back because it's the reflected mode, it will reflect back. While the transmitted, it was going through the, so what we here in the transmitted way, we have put the objective lens in after the light source. This is the light source. From the specimen, we can say in the transmitted they are opposite, but in the reflected way, the specimen reflect the light. It reflected back. So the objective lens will put it onto the same side. So if we talk about the reflected mode, this is our specimen. This is a light source, let's say. It shines the light onto the specimen. And now here is the objective lens. So the second option is the correct one, right? Now the transmitted microscope is only used for the opaque material. What do you think? Is the option C is a true or false? Is it correct or incorrect? They are saying that transmitted microscope we will use for the opaque material. You can always write in the chat box what's your opinion. Can we use a transmitted microscope for the opaque material? The answer is no. We want that light to transmit through it. If the specimen is opaque, we cannot pass light through it, right? So this is the incorrect one. D. In the transmitted microscope, light source and the objective lens are on the same side of the specimen. Transmitted microscope, this is the one which we talk about. The light source, this one, and the objective lens, this one, are on the same side of the specimen. What do you think about this? In the transmitted light, so this is obviously incorrect, right? So we can say that it's true. It's a cross. So in all these cases, only the option B was the correct one. The remaining all were incorrect. Right. So with that, we have solved the question number 1. If there is any doubt in this particular question, please let me know. If not, we'll move to the next question, question number 2. Okay, since there is no doubt, let's move to the question number 2. Yeah, let's read the question. The question is saying that which optical microscope mode generate better contrast? We want the better contrast. Which one is going to generate the better contrast? Bright field, dark field, oblique illumination, or both bright and dark field? So here we can see that among the option 1, A, and the second one, which one is generating the better contrast? What do you think? Here, among these two, the first image and the second image, which one is having the better contrast? The contrast is a dark field, right? Very good. Riyamul, that's right. So in the dark field, we can say that it's generating the better contrast because the background intensity is 0. More or less, on average, it's 0. So the specimen intensity of the specimen minus intensity of the background divided by average intensity. This is what we call the contrast. So now if we can minimize it, so we can increase the contrast. Okay, negative term, if we minimize it, we can increase the contrast. So in that way we can say that dark field is a better. And this is the reason why we are using it, because it's giving the better contrast to us. Our human eye is more sensitive towards the contrast, right? So in a class we have learned that the contrast should be, for human eye, contrast should be more than the 10%, more than or equal to the 10%, then only we will be able to detect it. If it is below that, we won't be able to detect that. Okay, so among all of this, the best option is the option B. Great guys, let's move ahead. Let's go to the question number 3. Which of the following material is best suited for transmitted light microscopy? Remember, in transmitted light microscopy, we have concluded that we need more or less transparent. Okay, if the specimen is opaque, we cannot see it in the transmitted light microscope. So what do you think? Among A, B, C and D, which one is the right answer? Biological tissue. That's the right answer. Very good. See, the reason is that the metal is again, so Rayamol has told us it's a biological tissue. The metal, we know it's very opaque. If we give, if we incident the light onto it, it will absorb, it will create some another phenomena. Ceramic is again the more or less large fraction of the ceramics are opaque. If we talk in the general way, okay. Again, you can say that I will thin it down, I can make it opaque. That's again the another way. But if we talk from the broad perspective, so we can say the ceramic is not the one. And the opaque polymer, the word opaque itself is there. So again, all these things is not suited for the transmitted electron microscopy. The best suited one is a biological tissue, because they are more or less they are transparent to the specimen. Sorry, to the light. So with that, we have solved the question number 3. Any doubt in this? Let me know. Since there is no, let's move to the next question, question number 4. Okay, question number 4 is more or less repeated. It's the same question only. Okay, let's go to the next question. This question is telling that which one is true for the dark field microscopy. Let's go one by one. Only direct beam is allowed to pass through the objective lens. So we are talking about the dark field microscopy. Dark field microscopy, we have seen over here that in the bright field, we let the direct beam to pass. In the dark field, we let the diffracted, or you can say that the scattered beam to pass. Okay. So here we can say that the first option, the only direct beam is allowed to pass through the objective lens. Is it correct? Option A. Option A, we know that it's not correct, right? Direct beam, if pass, then it's a bright field microscopy. Let's go to the second one. Both first and the second order beam is allowed to pass through the specimen. What they are telling that? See, this is a first order, and this is a second order, and this is a zero order, a zeroth order. What we have known that, what we concluded from entire thing, that we are letting in the dark field mode, we are only letting the first one to pass. This is a dark. So in the dark field, see, when we are doing the diffraction, so what we are getting the multiple order of the diffraction, the first order, second order, third order. But what we know that second order, third order, they are far more less intense compared to the first order, right? So further order, like these things, they will not generate the image properly, because the intensity itself will be very extremely low. So we are using the first order diffracted one. Okay. So this question is telling that both the first and the second order beam is allowed to pass through the specimen. Sorry, it should be objective lens. Okay. Option C, only diffracted beam is allowed to pass through the objective lens, right? That too the first order. The zeroth order and the diffracted beam is allowed to pass through the objective lens. Again, it's incorrect. Zeroth order mean that the direct beam, like that, the reflected. If this is passing, it's a bright field. Okay. Any doubt in this particular question? If there is, please let me know. Since there is no doubt, let's move to the next question, question number 6. Yes, the option C is correct. So here, the specimen with the large thickness and the transparent specimen respectively are required for large thickness and transparent specimen. Large thickness and transparent specimen. Okay, we are talking about the two different conditions. A transmitted beam, reflected beam and transmitted beam. Okay. So can we use the large thickness in the transmitted one? No. For the transmitted microscopy, we need the thickness to be as small as possible. A reflected light microscopy only. For the reflected light microscopy, we are not using the transparent specimen. Or else what will happen, the light will be will transfer through the specimen, and we will not be able to see. The reflected light will be very less. So again, it's incorrect. So now the transmitted microscopy will require large thickness. Reflected light microscopy, transparent. Again, incorrect. So large thickness, we know that it is required in the reflected one. and the transparent specimen is required in the transmitted. So the right answer is here is option D. Okay, so I hope it's clear. So more or less we are trying to, till now we have concluded that okay, under what condition the transmitted optical microscopy will be used, and under what condition the reflected light microscopy will be used. Let's go to the next question. This is a true and false type. The first one. Transmitted light microscopy is commonly used for studying the biological tissue. Riyamol has already told us that it's a correct, so it's a true, right? So here we can say that option A is the right answer. Let's go to the second one. Dark field microscopy provide higher contrast by increasing the background intensity. See, dark field microscopy provide the higher contrast. This is true. Next thing is telling that by increasing the background intensity. If we increase the background intensity, then will the contrast be more or will contrast be less? So the right answer for this will be whether it's a true or false. We know that if we increase the background intensity, then it's not going to contribute. Okay, like more or less the contrast will decrease. So we need the background intensity to be as low as possible. Not by increasing, we can say that by decreasing. So here the answer is false. To make it true, we can write the decreasing. Okay, let's go to the next question. Reflected light microscopy is also called metallurgical microscope. The answer here is true. Now why it is true? Most of the metallurgists they deal with the specimen which are opaque, and so the reflected light microscopy is the one which is quite beneficial for them. Like for me, I never use transmitted electron microscopy, and I'm a metallurgist. I am only using the reflected one. Now let's go to the next one. The bright field microscopy relies solely on the diffracted beam for the image formation. Bright field microscopy, it will rely on the diffracted beam. Is it true or is it false? What do you think? We are talking about the bright field microscope. Okay, so in the bright field, whether it will require the diffracted beam or we are using the reflected one directly. See, again we'll stick with our diagram. This beam we are using for the direct, okay, bright field. Remaining we are using for the dark. Okay, sorry, not remaining, the first one we are using for the dark. So here what will be true here? The bright field relies solely on the diffracted beam for the image formation. Answer is no. Not diffracted. It's the reflected one. Okay. The direct one. Okay. So the answer here is false. Okay, that's right. So now the last one. The human eye can detect the contrast difference below 5% intensity variation. So what do you think? We have discussed about it. The human eye, we know that in the class it's a false, right? That's good. It's more than 10%. The contrast should be more than 10%, more than or equal to 10%, then only we will be able to detect, or else no. So with that we have solved this entire question. If any doubt in this particular question number 7, let me know. If not, we'll move to the question number 8. Reflected and diffracted, both will be used in the bright field, right? More or less, see, the way they are, the angle at which they are happening. So in the reflected one, what we are seeing that the specimen will reflect your things, while in the, see here, it is reflected back. Okay, this is what we are using. So let's say we pass 100% of the intensity, 100% of the light. Out of that, 84% is the one which is carrying this first one. And this is the one which is going to be used for the reflected, what we can say in the bright field. Remaining, they are the scattered one. Since they are scattered, their angles are quite will deviate a lot from the direct beam, from this particular one, okay, from the reflected. So they are not going to be contributed. So reflected and the diffracted both will be used in the bright field. The answer is no. Only the reflected one is going to be used. While for the dark, while for the dark field, we are going to use the diffracted one, that to the first order. Okay, I hope it's clear. So now let's move to the next question. Question number 8. Now here, in dash microscopy, the condenser and the objective lens are on the opposite side of the specimen. We have we saw this. We're talking about the transmitted, right? Very good. While they are on the same side if we are using the reflected microscopy. Okay. So with that, question number A is over. Now let's move to the next question. Question number B. Dark field microscopy enhances the contrast by blocking the dash beam and using the dash light. So now, dark field microscopy enhance the contrast. How it is enhancing the contrast? By blocking the direct beam, or we can say that the reflected beam. And using the diffracted light, or we can say that the scattered light. Okay. Okay. Now let's move ahead. Let's move ahead to the next question. The Euler illumination used a dash lens to create a virtual light source. This is something which we have learned in the last class. We know that the Euler illumination, see, this type of illumination is not there in normal optical microscope. For example, I told you last time, I showed you one optical microscope last time. There, the Euler illumination was not present. The component which make this Euler illumination, like the arm microscope, to follow this Euler illumination is the converter lens. The converter lens is placed in front of the light, the light which is there, which from which we are illuminating the specimen. Okay, it will place in front of that, and it will convert entire thing to a single point. So it is going to create a virtual light source. Okay, and that virtual light source, because of that, we are going to get better, what we can say, better control over the microstructure. Okay, we can visualize it much more in the better way. It uses the collector lens, whose task is to collect the light from the source and converge it to a one single point, which is we can say the creating the virtual light source. Okay, with that, the option C is done. Now the minimum contrast detectable by the human eye is approximately -%. This we have talked multiple times. So what do you think? Had anyone remember what's the minimum contrast we can see? Yeah, so it's a 10%. Very good. Let's move ahead to the last option. In dash microscopy, the opaque specimen are studied using the reflected light. Is it the transmitted or it's a reflected? We are using the opaque specimen. What do you think? The opaque specimen, very good. So we can say that it's a reflected microscopy. Okay. So with that, we have solved this question number 8. Is there any doubt in this question? The entire thing that we have discussed, that the bright field and the dark field that we have discussed? Since there is no, let's move to the next question, next concept. So now what we have learned is that, see, our first part is over. We have discussed about the bright field and dark field microscopy. Let's discuss about the phase contrast microscopy. After that, we'll try to solve a question based on them. So now the phase contrast. This phase contrast, see, we know that the entire wave, all the waves that are there, let us say this is my initial wave. Let's talk about the dark field. In the dark field, what we do, the intensity of the thing is getting down. So what we are getting that, if I'm talking about the final wave, the amplitude will get down. So whatever the amplitude which I had here, the amplitude will be less. Because the diffracted beam we are there, right? The diffracted beam having the less intensity. It's all the group of the wave that is combined together to interfere together. It gives us the intensity which is visible. Now, in the phase contrast, what is happening that this is my initial wave. Now, what will happen? There will be some shift. So let's say now our the phase has been shifted. Okay. So initially there is a shift in the phase. So now whenever there is a shift in the phase, we can say that it will either lead to the constructive interference or it can lead to a destructive interference based upon the path difference between them. This phase difference is the one which is separating the dark field microscopy with the remaining three: phase contrast, polarized light, and differential DIC microscopy. Okay. So in the first one is what is happening that the amplitude of this particular wave is getting reduced. While in the remaining three things, in some way or the another, we'll see that what manipulation we are doing, that the things is changing from here to here. Okay, from here to here. And now this phase difference which is there, now it will give us some contrast. And this is what we are calling the phase contrast. Okay. Like this contrast can be used in all these three are only telling about this type of contrast itself. Okay. Now one more thing we have to understand that our eyes is not sensitive toward the phase difference. Our eye is not sensitive toward the phase difference. Our eye is sensitive towards the intensity, the contrast difference. So since we know that the path difference will be there in these two waves, so the interference phenomena is going to play. So that the interference phenomena is going to convert this phase difference to the intensity, the brightness will be the intensity difference, and like the constructive interference will give the bright, the destructive interference will give us the black. And that is something which is visible to us. Remember, we just talked about that the contrast is something which is visible to the human eye. So this is the principle. So now let's see that what is happening over here. How this is done. From here we can say that the light is there, the light is coming. The light is going to this particular condenser annual is there. It is only allowing these particular things, like let's say we are placing the light. What will happen? It will disperse the light in all the direction. Now if you put the circular ring opening to it, what will happen? That it will go into the cone. It will form the cone. Inside is a block. So what we are seeing, the light ray, the path is the hollow cone. Now that hollow cone is the one, see, we can see these are the one. These are going to the condenser lens. Now again the condenser lens will do the same thing. It will condense the entire thing to the specimen. This is our specimen. Now from here it will go to the objective lens, and the most important, the magic happening is over here, the face plate. Now this faceplate, what is doing that? The diffracted beam, the beam which are diffracted. So now see, this wave has went to the specimen. Two things can happen. First thing is that ray can diffract. Second thing is that no diffraction is there. If no diffraction is there, they will follow the same path. So they will follow the same path and it will go to the this one, the black one, the black region. It's quite thinner comparatively. Here, this one is quite thicker. The white region is thicker. See, whenever we have studied in the 12th standard that whenever there is a path difference, which is the thickness also, like if one wave is passing through the thicker one, another is passing through the thinner one, it will lead to the phase contrast, right? It will lead to the phase difference. So this phase plate is creating the phase difference. So the non-diffracted, the beam which is not diffracted, it's not deviated from the path, it is going to pass through this black one. And the beam which is deviated from the path, it is going to pass with this white one. And now here, it is going to add the path phase difference to them because of the thickness of this particular phase plate. Okay. So let me tell you, it is going to add the phase difference of lambda by 4. The beam which is passed through this particular, the black one, and the beam which is passed through the white one, they will differ by the lambda by 4 just by the plate. Now samples should also do something, right? Now, if let's say the specimen is having the more refractive index, there is some point in the specimen which is having the more refractive index. More refractive index means that it is going to create the more path length. The path difference will be even more. So it's going to add something to this. And if that is more or less, if it is near to the lambda by 2, it is going to cause a destructive interference. So the more is the refractive index, it is going to add something to this, it will cause a destructive interference. While if it is less, lambda by 4, it will give some intensity to us. Okay, it will give some white, it will have some amplitude, it will have some intensity. Okay, so in this way our specimen is going to react. The phase plate is adding the phase difference of lambda by 4. We just need one more lambda by 4. If the specimen is creating the lambda by 4 at particular region, that region will appear to be darker. If it is not, that will appear to be the white. This is the entire phenomena what is we are going to see. Keeping this in mind, let's try to solve few questions. Always remember this phase plate is something which we have added here. The question number 9. In phase contrast microscopy, what property of the light is primarily manipulated to create the contrast? What do you think? In the phase one, which property of the light we are using to create the contrast? Wavelength, intensity, phase, polarization. A, B, C or D, which one is correct? In the phase contrast microscopy, which one we are using? Which property of the light we are manipulating to give us the contrast? Whether it's a wavelength, intensity, phase or polarization. Very good. It's the option C is the right answer. We have seen in this particular thing itself that these three are based on the phase. Okay, this one is based on the amplitude. So in the phase contrast we have saw that it's a phase difference between the wave. So the right answer is option C. Very good. Any doubt in this? If no, let's move ahead. Let's move to the question number 10. Which component are the part of the phase contrast microscopy setup? So you will see this type of question in your exam, and you can also see in the assignments. Okay. Which component are the part of the phase contrast microscopy setup? Annular ring, phase ring, polarization filter, coherent light source. What do you think? Which component are the part of the phase contrast microscopy setup? This phase plate is also known as phase ring. Okay, so in this particular entire setup, we can say that the phase ring is the one is a part of the phase contrast microscopy set. So the option B is the right one. Okay. Okay, let's move ahead. Let's go to the next question, question number 10. Sorry, question number 11. Which optical component is required in the objective lens system for the phase contrast microscopy? Guys, there is one thing. There is one thing. The phase ring. The phase ring is the one. It's the right answer. There is one more thing. Which component are? I see. I made a mistake over here. R part of the phase. Okay. This condenser annular, and here we are using the annular ring. They both are the same. Okay. So they both will take part in this particular phase contrast microscopy. We have added two things. We have added this phase plate and we have added this condenser annular. Okay. So now we have got a question. Why we are using the annular ring in the initial? This one. To create the hollow cone. Okay. See, let's say we are not creating the hollow cone. In that case, what will happen? In that case, let's say the hollow cone is not created. The beam which is diffracted and the beam which they will, what will happen that they will pass through this also. So there will be a leakage. So now what we are doing is that in this entire setup, what we did, let us say I'm drawing the face plate. Let's say this is a face plate. This dark section, it will lead to the passage of, like it will only allow the non-diffracted beam to pass, while the remaining part, it will allow the diffracted one to pass. It is because the geometry that we have created initially, the ray. Now, instead of hollow, let's say we have the all solid cone of the light. In that case, what will happen? That since we are not creating any difference, we are not creating any particular ring, so there is no use of it. What will happen? That even the diffracted part will pass through this. Even the non-diffracted parts will pass through this. So the initial aim to separate, the more the important is this, the same. They both have equal importance. Okay. If you are not creating hollow ring, if you are not creating the hollow cone, then you are not going to, then there is a diffracted and non-diffracted beam. They will not be separate out. They will follow the optically, like the path, which are more or less, we can say that the bright field more or less it will give. The information which you are going to get, if you are not going to use this, and still if you are using this, it's more or less it will give you the bright field microscopy type of image. Okay. So this is the reason. The way the optics has worked, the way we have designed these things, for that only the separation in the diffracted and the non-diffracted beam will occur, or else it will not occur. Is it clear? Okay. So see, now let's say that let's take the two condition. Let's say that see, solid cone. Can we say that if I have a hollow cone, if I have a hollow cone and I integrate that, I can make the solid cone. Is it true? If I integrate this, we can make it solid cone. So we can say that the solid cone is nothing but an integration of each hollow cones with it, right? So now, instead of considering the solid cone, I will say that, let's say this is my solid cone that has been created. So I place the light is diverging it's spreading in all the direction, and I am getting a cone which is like only the diaphragm. This diaphragm is alive. Okay, let's say that there is nothing here. It's the solid, that normal aperture which we use, normal aperture. In the case of normal aperture, we'll get the light in all the different directions passing through this, so we'll get the solid. Let us consider that this beam, let's consider this section of the solid cone and this section of the solid cone. Let's say they have some certain thickness, so they are the two different sections. Now let us say that in the ideal case, in the real case, what we are doing, that this cone, this the light which is coming from this particular section is nothing, is something which is this is what doing. But what you have said that let's say we are using the solid cone, what will happen in that case? Let's say I am using this one also along with that. Let's say I'm taking the two hollow section, two hollow cone. We can understand with the two. Similarly, we'll apply with all of them. You can say that okay, we have integrated things and the concept we have understood in that way. So let's consider this two. So now for this face plate, so now we are having the face plate also. Face plate is having some thing over here. This is the one which is letting the non-diffracted beam to pass. So let us say that initially for this one, the first case. For first case, it is letting the non-diffracted beam to pass. So will it also let for the second case, same ring can I use, or will their optic will be different? See, for the smaller one, the optics can be like this. It will go like this. Sorry, I should have used the black color. For the smaller one, the optic will go like this. While for the larger one, the red one, the optic will go like this. Let's say after interacting with the specimen, none of them got diffracted or anything. They are following their same path, so the objective lens will try to focus. So this will focus over here. Let's say the first one, it is going to focus over here, and it will form this particular ring. Through this particular ring, non-diffracted beam. Both are non-diffracted. Both are non-diffracted. So for the first case, let's say this is the one. This ring can be used to pass through it. It is letting only non-diffracted beam to pass. So what will this ring also let the second one to pass, or their optic will be different? What do you think? Will the optics will be different, or will it be same? Like, can it pass through this? See, it will have some different convergence, right? So if I take a section, this section will need this ring to pass, and this section will need this particular ring to pass. So now what is happening? This was the region which is letting the diffracted beam to pass. This one is letting the diffracted beam to pass, but due to the thing that we have created, this thing is also passing through the diffracted beam, even though it was not diffracted. It's still passing through the diffracted region. Is it that we won't be able to create a part difference that will lead to the phase contrast, right? You will create a part difference, but with the different ring. With the same setup, if you are using all the entire cone, you cannot create. So what we can say that, see, our design was that diffracted beam should pass over here. Non-diffracted beam should pass through this particular region. But if I am using the bigger cone also, the larger cone also, what is happening that even the non-diffracted beam is passing through this. Now you are not able to create the difference. Now you are not knowing that which region is passing through what. So that's the reason why the entire purpose of this face plate, which is going to create the part difference of lambda by 4 between the diffracted and the non-diffracted beam, is not going to happen. Let us say the diffracted beam and non-diffracted beam both are passing through this. What will happen? They are passing through the same region. The path difference will be zero. The path difference between the phase, the diffracted and the non-diffracted beam will be zero. There is no path difference, so they will always form the contractive interference. You will always get the bright light, right? So to avoid this leakage, the leakage is that, what is the leakage here? The leakage is you are allowing the non-diffracted beam to pass through the region which is diffracted, which was meant for the diffracted. So since there is no path difference, we are not able to generate the path difference. That is the reason why we are not able to see anything. Sorry, we will only see the bright spots. Okay, and this is something which is happen in the defects known as halo. Okay, there what is happening there? See, this thing cannot be everything we try to achieve. Nothing can be ideal. So that's why what is happening, some leakage is happening, and that leakage is what which is leading to the formation of the halo, which we have saw in the class. Okay, since it's clear, let's move ahead. So for the question number 10, we can say that the annual ring, which we have discussed this far, and the phase ring, they both are the part of the phase contrast microscopy. Okay, so question number 10 is over. For the question number 11, we have seen that the phase ring is the one which we are using with the objective lens. Okay, this was the objective lens. With that, we are using the phase ring, phase plate. Okay, let's move ahead to the next question, question number 11. Sorry, question number 12. So in the positive phase contrast, don't get confused something like the positive and negative. Like whatever we have discussed till now, it's a positive phase contrast. Whatever we have discussed, the entire scenario which we have discussed is a positive phase contrast. The region with the higher refractive index will appear brighter, darker, colored, the same as the surrounding. What do you think? See, we have already saw that the phase ring is going to produce the path difference of lambda by 4. Now, if the refractive index is higher, mean that the path difference will further increase, right? So instead of lambda by 4, it will go to the more, let's say it will, if it reach to the lambda by 2, lambda by 4 to lambda by 2, it will give the destructive interference. Very right, that's good. So the right answer is option B. Okay, so for the 12th one, we can say that the darker one, it will generate the darker. So the higher refractive index will generate the darker. Clear? Okay, this is for the positive phase contrast. Now let's move to the next question, question number 13. By the way, any doubt in this? Any confusion in this? Since there is no, let's move to the next question, question number 13. See, halo formation, we have just talked. Fluorescent microscopy, no, we talk about this particular thing in the phase contrast microscopy. And the halo formation will happen in the phase contrast microscopy only. So what is happening that just a minute, guys. So now, let's say this is a biological cell. So at the edge, what is happening? This cell at the edge, it will appear very brighter. This is an artifact, as we have discussed. See, so what we were discussing that if we let diffracted and non-diffracted beam both to pass through the same thing, what will happen in that case? They will interfere constructively. There is no path difference between them. If we are letting them to pass through only one region, then there is no path difference between them. Since there is no path difference, they are going to more or less correspond to the brighter. Okay. So in that case, this is a leakage. The halo formation is nothing but it's more or less defects, or we can say that it's a leakage happening at the periphery. Okay. So this is something which we have observed in the phase contrast microscopy. No need to go in the more depth of this. It will itself is a very vast topic. Okay. So whatever we have discussed till now, that is beneficial. Now let's move to the next question. Question number 14. Which of the following statement about the phase contrast microscopy is true? First one, it rely on the staining technique to enhance the contrast in the specimen. Staining means that, see, something is get onto our cloth, we say that some stain is there. So, so are we adding anything to the specimen, making it to appear more contrast? Till now, whatever we have discussed, we are not doing this. It required the use of the fluorescent filter to visualize the specimen. Fluorescent filter, will discuss what it is. Till now, what we have not discussed. Fluorescent filter, we have discussed in the class that it will allow certain type of radiations to pass through it and certain type of radiation to not pass through it. This is something which we are not doing it. It is not suitable for the living cell imaging due to the potential damage for the light intensity exposed. So the light intensity exposed is not that much. It is primarily used for imaging of the transparent or unstained specimen. So the right answer is option D. In a large section, in a large way, we are using it for the imaging of the transparent or unstained specimen. Okay. So we are not applying anything on the specimen. While in the fluorescence microscopy, we apply something onto the particle, onto the specimen, so that they react and the fluorescent will be generated. The light will emit. Okay. So with that, we have solved this question number 40. Guys, again, I'm telling, if any doubt in this entire section that we have discussed, please let me know. If not, then let's move ahead. Let's go to the question number 50. Yeah. True and false. Guys, try to respond in the chat box whether the answer is right or wrong. The phase contrast microscopy work well for the thick multi-layered specimen. For the thick multi-layered specimen. Is it true or false? Just now we have discussed that it should be used for the transparent. So what do you think? If I'm using the thick and multi-layered, will it be transparent anymore? It won't be, right? It's a false. Very good. Now let's go to the next one. The human eye can directly detect the perceived phase difference in the light wave. Can we directly see that? Can we directly able to get that the phase difference? Very good. It's a false, right? Whatever the phase difference is there, now that phase difference, the beautiful phenomena of interference will take part into this. Now it will generate the brighter and the darker spots. Interference phenomena is there, and that is something which we can detect. We can detect the bright, we can detect that contrast in the specimen, contrast in the image, not directly the phase difference. Okay, so the answer is false. Let's go ahead. Biological cell shows poor contrast in bright field microscopy due to the minimum light absorption. Biological cells show poor contrast in the bright field microscope. Now we are talking about the bright field microscope. Due to the minimum light absorption. It is true. They do not absorb much. Their absorption is very minimal. So we cannot use the biological cells to see it in the bright field microscope. You cannot get a clear picture. It's more or less, it will look something like what I have showed you in the initially. Even though right now I'm telling you about the ceramic, but you can say that more or less the contrast will be very low because their absorption will be very less. Okay. So the answer is true. So you cannot use. Why? You can use these biological cells. Because the different section of the biological cell, first of all, the thickness variation is there in the biological cell, and also the refractive index will change. Due to this, due to the difference of the refractive index, due to the difference in the thickness of the different section of the cells, you will be able to visualize it. Okay. भैया थोड़ा yeah. So due to this difference, the phase contrast is there. So we can easily the phase contrast microscopy is very much beneficial for this biological cells. Okay. Now let's move ahead. The phase ring is located in the condenser lens system. The phase ring is located in the condenser lens system. True or false? Very good. It's a false. So we know that it's located in the objective lens system. Right. In the condenser lens system, what is located? In the condenser lens system, condenser annular. So annular ring is there. So instead of the phase ring, if we would have wrote the annular ring, then we can say that the answer will be the B. Or instead of writing the condenser lens here, if we write the objective lens, then the answer will be the okay. Now let's move to the next one, the last one. The positive phase contrast make high refractive index region appear brighter. What do you think? The positive phase contrast make high refractive index. Positive phase contrast make high refractive index. If refractive index is higher, then it will be brighter. No, it's darker, right? So this is what it is. So more or less, okay, only one answer is false, two remaining all are false. Very good, guys. I'm happy that we are able to follow things. Now let's move ahead. With that, our second section is over. So here we can say that the bright field and a dire field microscopy we have discussed. We discussed this section. We have discussed about the phase contrast microscopy. Now the third part we have to discuss about the polarized light microscopy. So the word itself is sufficient that we are going to polarize the light. Okay, we are going to use the polarized light. So here what is happening, that you have a luminescent source. It is producing the wave in all different directions. This thing we have already been learned. We are just brushing it off quickly. Okay. So now it will pass through the polarizer. So now polarizer will do that. Okay, only one particular set of the vibration particular plane will allow. Let's say this one. Okay, so out of this only this will go. Now this is the one which is going to interact with my specimen. Okay. So again here we have in the class we have known that the specimen should be anisotropic. If it is isotropic toward this particular light, it is not going to show the information which we are seeking. So now once this light go to the specimen, it's split. It's split in two parts. Okay. The physics is quite complicated, that why it is happening. So we are not going in that. Now since it is splitted, it's going to two different paths. Since it is following two different paths, we know in our specimen, different section, different region will have different refractive index. They will have different refractive index, different contrast. Even if you consider that you have the polycrystalline material of the same phase, there is no multi-phases there. Different grain orientation is there. That orientation, each orientation will behave differently to the light. Their refractive index will change based upon the orientation. Now that orientation information you can extract. So now one section is passing, one of the light, let's say, passing through the one region, another is passing through the another region. And with that we can say that, okay, of the path difference. Now this light, once they come back, they will again combine with each other. and they will tell each other that, okay, what difference they have faced, and that is something which we are going to see onto the screen. If the difference is like in the thickness, that will also be not thickness is not that much over here. If the more different refractive index is there, then they are going to be they will show the information. Okay, and yeah, sorry, thickness will also be there. It's just that we are not able to see the 3D image of it, but we can see that the refractive index and the thickness will be there, and also that we know in the material, if it is anisotropic, different direction will give the different refractive index, and that is something which is going to be which we are going to see in this particular entire polarized light microscopy. Okay, so now if any doubt, let me know. If not, let's try to solve a question based on this. Okay, yeah, here the question number 1, sorry, question number 16. What is the primary purpose of the polarized light microscopy? For now this entire thing, what is the primary purpose? To enhance the magnification, to enhance the contrast in the bifringent material, to reduce the specimen thickness, to eliminate all optical artifact. Bifringent material, they are anisotropic material. Anisotropic material, they will behave differently to the light when the light has been passed in the different direction. So now while in the discussion part, I told you that this material is anisotropic. It should be anisotropic. If it is isotropic, all the path will behave same. So there won't be any change in the refractive index and all those things. Okay. So the right answer here will be the option B. To enhance the contrast in the bifringent material. Okay. Any doubt? Let me know. If not, let's move to the next question, question number 17. Here, which two essential components are required for the polarized light microscopy? Polarized light microscopy, okay. Phase ring and annular ring? Incorrect, because phase ring and the annular ring we have learned that it is required in the phase contrast microscopy. So, option A is incorrect. Uday, Riyamul, Gitu, yeah. Yes, very right. It's a polarizer and analyzer. And condenser lens and objective lens, that is there, but two essential components which we are talking about. Okay, so right now we'll talk about the most correct answer is this. Okay, lambda plate and the dark field stopper, no, again it's not. Okay, the condenser and objective lens, see, condenser and objective lens you will need everywhere more or less, but here, see again, here we have the condenser lens, we have the objective lens. So one can also say that, okay, this is also the right answer, but we are talking about the essential components. So if there is only one selection answer, I will only go with B. If multiple choice are there, I will go with B and C. Okay. Okay, very good guys. Question number 17 is done. Let's move to the next question, question number 18. Which property of the material make them suitable for the polarized light microscopy? High refractive index, bifringent, fluorescent, opacity. What do you think? B, right? Very good. Bifringent material. Yeah, very good guys. The answer is B. Let's move to the next question, question number 19. What is the function of the lambda plate in the polarized light microscopy? So this is a lambda plate. So now what is its function? Let's see the option and we'll try to understand. To polarize the incident light, to convert the phase difference into the color contrast, to increase the magnification, to reduce the glare. See, we have saw that in a class, like different grain having the different orientation will appear differently. Okay, they will have different color. This color is something which is given by the lambda plate. See, the physics is quite complicated, but I will tell you why the lambda plate, the lambda is given. To one of the light, So what it do, it add the lambda, the path difference to it, the lambda path. Okay, that is 2 pi. So it will make one of the wave to go more ahead of the another wave, and it will create one of the light to be the reference one. Again, the things are quite complicated. All we need to understand that the lambda plate is something which is going to make our specimen, the orientation, instead of grayscale. If we don't use the lambda plate, we will get the grayscale image with the different contrast. Different orientation will have different contrast. But again, the contrast is not like, if they are very close to each other, then it will be very difficult for us to identify whether these two regions are two different grain or not. While if we use this, if we add the color into them, it is quite easy for, it will be quite attractive, pleasant for us to to see the microstructure and to analyze it. So the right answer is option B. The entire purpose of the lambda plate is to add the color contrast to this. Okay, so if you don't use, you will get the grayscale. If you are using it, you will get the color contrast. Okay, so this was the question number 9. Any doubt, let me know. If not, let's move to the next question, question number 20. Which of the following material would not show birefringence? Calcite, quartz, cubic crystal, and apatite. See, A, B, C, and D. Among all of this, we know that we cannot use this, which is not birefringent material. It should be, it means that it's anisotropic. What about the cube? If we talk about the cubic crystal, they are isotropic. Remaining the structure of A, B, and D, they all are anisotropic. So only the which one is not, which one we cannot use is the cubic crystal, because here all the directions are the same. Okay, so it's an isotropic. So, and we will only use this like this birefringence. It's for the anisotropic material. Let's move to the next question, question number 21. Guys, let's try to answer this. What caused the colorful pattern seen in the polarized light microscopy? The different wavelength being absorbed, optical power difference converted to the color via interference, fluorescence of the specimen, surface reflection. What do you think? What is the right answer? Uday, option B. Riyamol, option B. It's right. It's option B. The optical power difference. So whatever the information that polarized light went through the specimen, it split it into two parts. Now these two parts are collecting the information from the specimen. Different region, different refractive index, different optical path. Now that optical path which we have got, that is going to be one which we are going to convert through the lambda plate to the color interference. Okay. So very good, guys. The right answer is option B. Let's try to solve few more questions. Not so far. We are about to finish. Okay. Maybe in next 20 minutes we can wind up. Let's try to understand things. What's here right now, that what happened when the cross polarization are used without a specimen. So now what they're saying, that entire thing you are doing, let's say we remove the specimen, what will happen now? No light pass through. The answer is B. Answer is B, right? No light will pass through. See, initially our first polarizer, what it did, first polarizer, we had this particular rays in different directions. The first one told that, okay, I will only allow this one. The polarizer and the analyzer, their orientation are quite different. Here also you can see that it's like this, and here it's like this. Analyzer is telling that only I will let this not vertical, or I will only let the horizontal one to pass. Since there is no specimen, there is no change in this particular wave, it is going to remain as it is same. So if we try to superimpose, like nothing will pass. Okay, this is a light source. This is what we will get after the polarizer. And here, if we see the image, it will be dark. Nothing will be there. It will be black screen you will see. So this is what we will get after the analyzer. Onto the screen you will see. So the no light will pass through this. Okay, all light will pass through this? No. So if there is no specimen, no interaction with the specimen, then it means that there is no path difference we are creating. Path difference leading to the phase difference. Phase difference can be analyzed with the help of their interference phenomena, and it will convert to the intensity. Very good. This, I hope it's clear, the question number 22. If it's not, let me know. Now, question number 23. Polarized light provide information about, no, what information we are getting? Regarding what? Multi-phase material, depth perspective of the material, fluorescence of the material, biological specimen. In my material, if two different phases are there, it means that two different refractive index are there. So on a larger scale, we can say that if my material is having the multi-phase, then we'll see that, okay, one phase in some one color, another phase we'll see in the another color. So multi-phase material we can analyze. Okay. Depth perspective we are not going to get. Depth perspective of the material, no. It's like the 3D information. No, we will not get the 3-dimensional information. The depth information you will get in the DIC, differential interference contrast. Fluorescence of the material? No, fluorescence again we are going to discuss. Biological specimen? No. Okay. We need an anisotropic material, that's all. The right answer is option A. Very good. Now, with that, we are done with the first three. The polarized light microscopy is also over. Now, we are going towards the differential interference contrast microscopy. Let's see whatever we have learned about this DIC. See here, we have this. This is what we have seen in the polarized light microscopy, right? So in the polarized light microscopy, this is there. Now, we are going to add few more component to this, and which will convert this polarized light microscopy to the differential interference contrast microscopy, DIC microscope. Okay. So what are the things? After the polarizer, before the condenser, we are going to put something known as prism. This what prism? It has particular more name. Other than this, there was Nomansky prism. Yeah, Nomansky prism it is. Okay. So now what it's going to do? The polarized light which we have got, it is going to split it into the two part. It will split it in such a way that one part will enhance and another part will be little bit behind. Okay, the part difference has been created in them. Sorry, not like that. It's a different. I confused with something else. So initially we pass the polarizer. Okay. Now what this is going to do? This is going to split it. It will going to split in the two part. This two part will be in such a way that they will be in the, but they have some property. They will be the same phase, but they will polarize by 90 degree. That is, let us say the first wave, the electric field vector is like this. This is I am talking about. Let's say this one. See, it's going here, it's going here, it's going here, it's going here. Let's say first one we are talking about. Now the second one I am going to make. In the second one, what will happen that it will more or less it will be like this. It will oscillate in the horizontal direction. But one thing we can see that they will have same path difference. Sorry, they will be in phase. They will not be out of phase. The same phase, but their orientation will be different. Right. Now, since they have different orientation, different direction, once they are going to interact with the specimen, this both wave. Now, see, instead of one beam, initially here one beam was going and the specimen was getting splitted and we are getting generating the information. Right now what we are doing, we are passing the two beam through it. This two beam, once they fall onto the specimen, they will have some path difference, like the, not the path difference, the physically they will be separated. Physical separation will be there. This physical separation is very important. They will be separated by 0.2 micrometer. In the class we have saw that okay, why 0.2 micrometer is there, the difference. Now this two will get onto the specimen and now they are going to interact. Now with that, different thickness will give us the different contrast. If the something high difference is there, then too also we will get the contrast over here. So here now again after that it is the condenser lens. Once it interact with the specimen, there is objective lens. After that again one more Nemansky prism is there, which is going to again converge them together. And after that we can say that the polarizer will be there, and after that a screen. Okay. So all that we have added here is this two stuff, this two prism. If we remove this thing, this is nothing but a polarized light microscopy. If you add differential interference contrast is there. Okay. So now the thing is that they are polarized in different directions. They have different orientation, right? So their refractive index will be different in the specimen. This one, the horizontal one, will show the different refractive index inside the specimen. The vertical one will show the different refractive index inside the specimen. And now after collecting the information within the specimen, they will come out, they will have some path difference, they will have some phase difference again. Whatever we have discussed till now. See, now you are able to understand that what is happening. In this entire, these three things, this and this, all we are doing is we are making some path difference, some phase difference by passing the light through the specimen. Once it pass through the specimen, they will have some information. That path difference, that phase difference is something which is carrying the information what is there inside of the specimen. Okay. And this was all about the TIC. Let's try to solve few questions. The depth perception of the pseudo 3D effect is provided by which mode of the optical microscopy? We told that it's going to give the polarized light microscopy was not giving the depth information, the shadow and all, like which one is at the top, which one is bottom. If some feature is there, we cannot see it with the polarized light microscopy. But with the help of DIC, we are able to see that. Okay, so the right answer will be A, B, C or D. The right answer is over here is option D. Right. This is the question number 24. See, in the exam also, in the assignment also, you will find the similar type of questions. Okay. Let's see this. In DIC microscope, the Nemansky prism split light into. Now here it's a good question. Two ray with the same polarization. Two orthogonally polarized ray. Three ray of different wavelength. Unpolarized light. What do you think? Among all this, which one is the right answer? Option B, right? Very good. So it's a 0 degree and 90 degree we have talked about. They will polarize in the two different way. So the right answer is option B. Let's move ahead to the next one. Question number 26. Which of the below are used in the differential, again, DIC microscope? Wilson prism, phase stopper, polarizer, analyzer. Which of the below are used? Okay. The question is R. Very good. Wilson prism. Option A is the right answer. Phase stopper, we know that we have used it in the very good Riyamul. It's A is the right answer. Phase stopper we are not going to use over here. C, the polarizer we are going to use, and D also, analyzer is also we are going to use. Very good. So with that we have solved this question number 26. See, few books, once they make the question about the DIC, they forget that the polarizer and analyzer is also there. They mostly focus on the Wilson prism, okay, Nemansky prism. So even if they put this question, they will say that okay, only first is the right answer. Okay. Even though this is a primarily correct, but these two are also present. We should not ignore their importance over here. Okay. So this is the question number 26. You will find such mistake while you do some assignment in this particular week. Anyway, we are going to correct that very soon. Now question number 27. What is the nature of the split polarized light by the first Nemansky prism? Split polarized light, okay. See now what they are saying that okay, after Nemansky prism you got two beam. What is their nature? What is their nature? Their electric field vibrate in the same phase. Option A. Their electric field vibrate in the same phase. Their electric field vibrate in two different perpendicular plane. Sorry. It was not phase, it's the plane. Their electric field vibrate in the same plane? No. Very good, the answer B is the right answer. So their electric field is going to vibrate in the different perpendicular plane. So this is what we have seen. The red one is the vertical, the black one is the horizontal. So they are going to vibrate in the two different plane. They are in phase, they are out of phase. Sorry. Very good, the right answer is here. They are in phase or they are out of phase? What do you think? Why is there any part difference created by the Nemansky prism? If the part difference is here, then they will be out of phase. If not, then they will be in phase. They are in phase. Very good to that. We have saw here that there is no phase difference in between them. They are in sync. They are in the same phase. That's right. They are out of phase? No. Last one. They travel along the same physical path. What do you think? The last one. Is it right, correct or incorrect? See, we have studied that they will be physically separated. Once the condenser lens condense them like onto the specimen, they are spotted onto the specimen, they will be separated by the 0.2 micrometer difference, more or less. This is something which is known as the resolution of the optical microscope on an average, right? So we'll separate them by that amount. So there is a physical separation is there in this particular way. They travel along the same physical path? No. They travel along the two different physical paths. If they travel along the same physical path, then there is no difference in the phase, right? They are going to travel along the same path. They will encounter the same material. They will encounter the same defect. There is no phase separation in them. There will be no part difference. There is no information we will be able to extract from it. Only if they travel along the two different paths, then only we will be able to extract the information. So this is incorrect. This is very important. The last one is very important. So the right answer is B, C, and D. Okay. Okay. Any doubt? Let me know. If not, let's move to the next question. Question number 28. Compared to the phase contrast, DIC microscope does not produce three-dimensional appearance, halo artifact around the edge, high contrast in the transparent specimen, sensitive to the optical part difference. See, one thing we need to get, like I forgot to point it out, but it's already been discussed in the class. When we discuss about the halo artifact in the phase contrast microscopy, there we saw that it is happening because of some leakage. The non-diffracted beam is passing through the region where it was not supposed to pass. Okay. While these things, like why it is happened, that we have created the physically different path for them. We have physically tried to separate them in the phase contrast. We put one annular ring, we put one phase ring. With the help of the phase ring, we try to separate them. But at the boundary of the separation, there will always be the leakage. Some problem is there. That thing is avoided over here. That thing we have avoided with the help of the Romansky prism. So this is correct. This they produce three-dimensional information. DIC produce compared to the phase contrast. DIC does not produce halo artifact around the right answer is option B. They both are sensitive to the optical path, okay, in their own way. Okay, so the answer D is not the right one because they both are sensitive toward the path. The difference is there that the hollow artifact which we are able to see around the edge, this is the very large, we can say that the overcome which we are able to limitation of the phase contrast which one can overcome with the DIC. The halo artifact will not be there in the DIC microscope. Okay. So now if there is any doubt, let me know. If not, we will move to the next question, question number 29. Oh, with that we have completed the DIC. So till now, whatever, whether it was this entire thing, we were understanding about the fit. In DIC, no phase change is there and hence no path difference, right? No phase change is there and hence no path difference. See, in DIC, whether it's a phase contrast, polarized light microscopy or the differential interference microscopy, in all these things, the phase change will occur. In the DIC, or we can say the polarized light microscopy, we have studied that anisotropic material having the different refractive index in the different direction, there will always be some phase difference will associate with them, because if the refractive index is low in one direction, refractive index is high in another direction, the way the speed at which the light will travel will be different, and that is once they come out, due to that difference of the path, that speed difference, there will be the difference of the phase, and that phase difference will correspond to the path difference. So in all these three, the thing which you have pointed out, it will be present in all the things. The phase change will always be there, whether it's a DIC, whether it's a polarized light microscopy, or whether it's a phase contrast microscopy. Okay, let me know if it's not clear. Okay, since it's clear, let's move to the next part. Now we are going to the fluorescent microscopy. Let's read about the fluorescent microscopy. Let's try to brush up whatever we have studied in the class. There is a light source over here. There is an object. The specimen is over here. We want to see this. This specimen is not, it's a fluorescent specimen. So now what is happening? Fluorescent. You are bombarding the light, the visible light onto the specimen. Now a specimen can do one thing. It can absorb it. Once it absorbs, the electron will go to the higher energy state. Right. Let us say there was some energy. The initial ray had some energy. Initial. Now our specimen has electron or something, some defect, something get excited to the higher energy state. Now they are coming back. They will emit it. Okay. More or less, in majority of the specimen, what happened that in this particular entire process, they will lose certain amount of energy. So the overall, the energy of the final which we are going to get will be less. Right. This energy is the one which we are going to, which is something which is like that has coming from the specimen now. We bombarded the light, we made the specimen to go to the higher excited state, now it will come back again. It happened in 10 to the power of minus of 12 seconds, right? Picoseconds. This the reversal of the higher energy state to the lower energy state. Okay, it's very fast. It's very fast. So this now this intensity, now what is happening? The light source we have provided, it is passing through the exciter filter. What exciter filter will do? It will only let certain particular fixed wavelength of the light to pass through it. Okay, pass through it, and now there is a filter cube. Sorry, this entire is a filter cube. In that there is a dichroic mirror. Very important. It's a very important one. Why it is that? The way it is behaving with the incident wave, it is reflecting. Now this incident wave went to the specimen, objective lens went to the specimen. Now the specimen generated, it absorbed the radiations. Now it's emitting it. The emission that is emitted, now it will go back to the same path. Now the thing is that this dichroic mirror will do the magic in such a way that it's reflecting the incident one, while it is transmitting the reflected one, the one which is emitted. And this is the entire the way it has been designed. That so this is one of the most important part in it. Okay. Now the barrier. Now again, this beam which is which has been came from the object, which is emitted from the object, it will pass through the barrier or emission filter, we can say. So this emission filter, again, it will only let certain particular wavelength to pass. Okay, so let us say in your specimen you have multiple wavelength, like, and like one of the object is showing the more energy, another is showing the less energy, but for a timing you only want to see the particular let's say higher energy one you want to see, then you will adjust it. If you want to see only the lower energy one, then again you will adjust it in such a way that it will only capture the lower energy. Okay, so this is the entire thing. Exciter filter will only let the certain particular wavelength of the light source to pass through it. Again, see, all the light we cannot use for the object, for a particular object. Okay, since if we keep on changing the object, the different object, different atoms, they will have different energy of excitation. So for them we will have a different wavelength needed, right? So this exciter filter will do that thing. If you adjust it, you will be able to adjust the incoming light that is striking to your specimen. So this is the entire part of the things. Now once it passes through this emitter filter, there is a screen. Now you will be able to see the specimen. Okay, it's mostly used for the biological specimen. Now biological specimen, one more thing, I forget to tell you that there is a fluorescent some fluorescent material is there, like something we have to, all the materials are not the fluorescent material. It's very rare that very less materials are fluorescent material. So now let's say someone is using it for the biological purpose. They want, let's say, nucleus is there, then the cells are there, they want to see how it is looking, how the nucleus is looking, how the cells are looking. They will try to add some chemicals into that, so that these chemicals will go stick to the nucleus or stick to the cells, like they will have different reactivity toward each of them. And this material which we are putting in the specimen, they are the fluorescent material, they will emit the light. Okay, so wherever since our specimen is behaving differently with a different section of the object, they will emit the light in such a way. Okay, somewhere the particle has stick more, they will emit more. You will be able to see the feature of that particular object around it. Somewhere the object, this particular the material, the paint which we have put, the fluorescent thing, it's less, then there will be the less amount of emission from there. With that you will be able to see the image. Let's try to solve a question based on this. Very fast excitation and the emission with lap, no time gap is shown by excitation and emission we are talking about. Okay, reflection we cannot, excitation and emission, this phenomena is not there. Now you will see that the fluorescence, this is also we have discussed in the class that sorry phosphorescence is something which will take a lot of time. It is like it will take around a few seconds, couple of seconds to disappear. Let's say you turn off the light, it is taking couple of seconds to turn off. Okay, while the fluorescent is the one, this phenomena, it will happen within a seconds, sorry, with 10 to the power minus of 12, like around picoseconds. So the very fast, no time gap, it will be shown by the fluorescent material. It's fluorescence, not the phosphorescence. Okay, so the answer B is the right answer in the question number 29. Okay, you agree with me? If not, let me know. If there is no doubt in this one, let's move to the next question, question number 30. Now, the key difference between the fluorescence and the phosphorescence is fluorescence required UV light. No. Phosphorescence show afterglow. Afterglow means that even if you turned it off, still it's glowing. Let us say here, instead of putting this fluorescent material, let's say I am pushing the fluorescent material right now. I turn on the light. I am seeing in the screen, okay, the brightness is there, I am able to see. I turned it off, quickly it will turn off here. There won't be any glow. Now I am using the phosphorescent material. Now what it will do? Light is going through the specimen, going to the object. Now once I turned it off, I am able to see the image, right? Now once I turned it off, still I will be able to see the image. It will fade away with the time. Okay, this is what phosphorescence is. So here phosphorescence show afterglow and the fluorescent does not. This is correct. The reason is the time. It is taking the 10 to the power of minus of 12 seconds. It's taking couple of seconds. One can say that around 10 seconds also it's take. Okay, so this is what it is. Fluorescent emit X-ray. Oh man. Phosphorescence is a faster? No. We are left with, I don't know. I don't think much question. Okay, we are left with a couple of questions only. Now, let's say this. The dichroic mirror in the fluorescent microscopy. What they are talking about this particular, the dichroic mirror. What it will do? What do you think? What is the right answer? A, B, C, or T? Let's read it. Reflect excited light, but transmit the emission light. Excited light, the one which we are passing from the light source. Transmitted light, transmitted emitted light. Like it will transmit the emission light. Is it true or false? Option A is the right answer. Very good. Transmit both? No. This is also incorrect. This is also incorrect. So here we saw that the light source, this dichroic mirror, it's reflecting the light source while it's transmitting the emission light. Okay. Option A is the right answer. Let's move to the next question, question number 32. Fluoropores. Fluoropores are those material which I talk about. Okay, they will go to the biological specimen. They will stick differently to this. Are used in the fluorescent microscopy to, first one, absorb all the light, bind to the specific structure and emit light upon the excitation, scatter light randomly, reflect light without absorption. What do you think? Among all this, which one is the right answer? The fluoropores, the material which we put, now it's going to stick with all the structure differently based upon their reactivity, based on their absorption. So the option B, bind to the specific structure and emit the light upon excitation. Okay, they will emit the light when we are going to provide excited light to it. Okay, so the answer B is the right answer for 32. If any doubt, let me know. Okay, with that, this is the last question for our today's discussion. The sample preparation for fluorescent microscopy often involve staining with the fluoropores, coating with a metal, heating to the high temperature, crushing the specimen. What do you think? What is the right answer? For the fluorescent microscopy, which one is the right answer? So yeah, it's staining with the fluorophores. Option A is the right answer. Okay guys, so this was all. This was a list of the questions that we have covered today. If any doubt in this, please let me know. I will quickly reverse back all the questions, all the concept that we have discussed. Just quickly have a look onto it and let me know if you face any difficulty in that. If you face any questions like in the class, like while attending that lecture, that also you can ask. So this was the list of the 33 questions that we have discussed till now. Let me tell you, few of the questions can appear in the final exam also, and similar type of question you will see in the assignments. So based upon the 5 different microscopy technique that we have discussed in this particular week, we have solved all the sections of the questions. Okay, so we have covered the variety among all of them. Okay, so this is also there. This question is on the phase contrast. These are the list of the questions that we have discussed about the phase contrast. The halo formation. Again, we are not going to the depth of this. It is due to the artifact that is happening, and it appears in the phase contrast, which you can avoid in the DIC. So with that, we have covered the entire section. I hope whatever we have discussed today will be beneficial for you. If you face any difficulty, you can always write in the dot solving forum, okay, discussion forum. There also we will respond. And the people who are not able to attend this particular class, for them the link will be shared with everyone. Like the YouTube link, the video will always be uploaded. Okay. So this was the list of the content. Then we discuss about the concepts over here. And with that, today's class is over. Okay guys, since there is no doubt, so we can wind up today's class. So I hope it's beneficial, and I hope to see all of you in the upcoming class also. Next week around 3, we can meet again. Okay, bye bye.